Good morning from Manchester and welcome to the UAV pilot's briefing. Here the experiment is done on the CG by moving it aft of the intended CG position. Observe the loads, and over here the experiment is done on moving them forward. Do notice the differences in reaction of the aircraft. There is greater tolerance in this case. You may pause the video now to see the values collected from Unity. On the top left chart, we can see that a higher flap setting allows for a greater CL maximum value. Other plots like drag polar and lift to drag ratio plots are specified as well. Here we can see for an elevator at minus 15 degrees, we hit origin on the CM versus CL graph on the right. Now moving on to the thrust test, we can see in this experiment that the aircraft hits 27 newtons, although it was calibrated for 30 newtons. Both charts show almost a perfect constant gradient, and this signifies good calibration. Moving on to the static calibration, this is now a test of the control surfaces and alignment with the correct intended direction. Now we're testing for the roll, we just reversed it. Now for the elevators, and now the rudder. Now testing for the flaps. The flaps were reversed. As you can see, all of them are demonstrated right now. The following tests are for two different CG positions at 25% and 35%. Here we can see that the 25% case has a much more stable response to a step input in the elevation. The same is done for the 35% CG value, and we can see that it's significantly less stable. The controls are much more sensitive for this case, and in some cases gets really uncontrollable and out of hands. We can also see the lift distribution denoted by the green arrows on the wings. Now the wind velocity was varied. This is at a high relative velocity, and you can see that the roll rate is pretty substantial. However, when the wind rate is reduced, the wind speed is reduced, now you can see that the green arrows have reduced in magnitude, and now the roll rate is much slower. To further evidence the static tests, this dynamic tests at the same CG positions provides even a graphical representation of certain values as they change. For the 25% case, we can see that it is damped pretty fast. The same at the 35% of MAC, we can see a step input has a much long-lasting effect on the convergence values. For the cruise trim test, we are trying to establish trim flight at 20 meters per second with obviously a constant altitude, as we are trying to achieve steady flight. We can see how that happens. We can also see slight maneuvering done in terms of the rolling of the aircraft in order to establish its steadiness. We can see that 20 is almost a constant value seen through this flight. With this experiment, we aim to understand the position of the CG in the vertical axes. Two positions of 0.05 and negative 0.05 were chosen, with negative 0.05 providing better stability overall. Now we move on to the free flight segment of this video. Here we look at the ground handling, and we can see at high speeds of approximately 20, which is when the aircraft would have taken off normally. It is uncontrollable and hard in general to handle it on the ground, as due to the terrain, the aircraft wishes to take off. We can also see it being unstable in the lateral direction as well. Here, looking at low speed taxi, on the other hand, we can see that it is a much more controllable aircraft, and the effect of the rudder and the nose gear is much more pronounced here. 10 meters per second is recommended. Now moving on to the minimum unstick velocities. This is with flaps, so understandably it should have a lower minimum unstick velocity. which as we can see here is at 15 meters per second. Performing the same test without flaps this time should have a higher velocity, and it does so at around 17 meters per second. Here the idea is to find the minimum trimmed flight speed. You may now notice that the aircraft is undergoing a phugoid oscillation in the way that it's an oscillatory movement. The minimum trimmed flight speed would be around 17 meters per second. Here looking at the maximum counterpart of it, and at 37 meters per second would probably be on the higher end of values for this aircraft. Moving forward, now we will do the phugoid analysis. Observing the graphs, we can see that the time period of the plots produced is 9 seconds. This translates to 0.11 radians per second or 0.11 Hertz frequency. Now we're going to continue with the full flight phase. We're going to first take off at 19 meters per second in this case and slowly bank towards the right side in order to get the first cone. The camera to follow would be the one on the bottom right of the screen, and the idea of this flight is to essentially fly through the cones in a rectangular manner in order to land back at the hangar. There are significant altitude changes, although this is only to ensure that the path is followed as closely as possible. This section of the flight is pretty stable, as can be seen at a constant altitude of 13 meters and about at 24 meters per second. The aircraft now banks to its left to follow the path, although it is interesting to note that G-loads experienced on this aircraft are significant, but it is not of any significant harm to the system as this is an unmanned aerial vehicle. Here the sensitivity of the controls were validated again in order to fly as close to the cones as possible and pull up at the right moment, continuing on with the flight plan. We now approach the landing phase, and obviously the vertical rate has to be as slow as possible in order to achieve a smooth landing. We can see some bounce, although that happened just once. And for this landing, brakes were not used, which is why there is not a significant reduction in speed. However, the friction from the terrain is enough to reduce this to a full stop. I thank you for your time.